Hello, Sackville. Happy holidays. I hope all is well. Do introduce yourself. Say hello in the comments. That'd be great to know that you are all there. I hope your week's been good. Some decent weather for a change, which is quite nice, really, isn't it? Okay, so today's plan is looking at computational thinking. Now, I think we're now getting into the territory that a lot of people find really, really hard. So this is looking at paper two now. We finished paper one. That was the legal, ethical, cultural, all that sort of stuff. Now we're into the tricky one, which is tricky for some people, this idea of programming and how you do it. And I think a lot of the reason people struggle with this is because they read the question once and think, oh, it just looks so hard. And then they give up. So I think if you are someone who finds the coding a bit of a difficult thing to do, the plan today has got to be to actually be able to get yourself 2 or 3 marks on these 6-mark questions, and then hopefully push that to 4 or 5 marks. But step one is to get 3 or 4 marks on it. So we'll look at how you can do that today. So we're going to look at building algorithms next week or the week after. But our plan today is to think about how you can actually approach this algorithms paper and make sure that you do score some good marks on it. Now, I've got some quiz questions. I can see there are 2 of you who are currently watching, but I won't do the quiz unless you guys are going to jump in and answer it, because I think it's just kind of pointless. So if you can have a look at that question, and this is a programming question again, have a look at this and see if you are able to come up with an answer. For I equals 10 to 0, step -3, print I. What is this going to output? That is my question to you. For I equals 10 to 0, so it's counting down. So you're starting at 10 and you're going to 0. In step -3, what do you think that is going to print on the screen? Any ideas at all? Like I say, I can see there were 2 of you. It's become 1. If you don't answer, that's absolutely fine. I'll jump on and just do the main block today. There's quite a lot to get through. So, yeah, I think it's time to go and do that. So I'll jump on to the next one rather than doing a quiz by myself, because I know the answers. So I'll go on to the next bit. Let's go to here instead. What's it all about? So, and by the way, if you do want to answer some quiz questions, let me know, because I can jump back to them really, really quickly. Today's work is about abstraction, decomposition, and algorithmic thinking. Now, on the face of it, this is actually really straightforward, because abstraction and decomposition you can summarize in 2 sentences. It's not hard. And they might give you some examples. We'll look at some example questions in a minute. But actually, this is a bit more than just knowing what they mean. It's also about applying this to the algorithm questions. So what's supposed to happen? The reason this comes just before algorithm design and algorithmic thinking is that abstraction and decomposition are really the 2 tools that you're going to use to design your algorithm. So if you just learn these two off by heart and then don't apply them to an algorithm, it's kind of really, really hard to actually write an algorithm that makes any sense. So this is 2.1.1, the first part of paper 2, and it's computational thinking. So computational thinking involves taking a complex problem, trying to understand the problem, and developing solutions. Well, so far so good. So they give you an algorithm question and you've got to write an answer. Easy peasy. And the key principles are abstraction, decomposition, and algorithmic thinking, although algorithmic thinking kind of encompasses the 2 that come before it, okay? So let's go for the quick definition. And sometimes they want you just to write this down. So this is what you need to know. And I would say particularly the first part of this, the first paragraph is probably, so it's only 2 lines. So abstraction is ignoring the characteristics of a problem that will not help us to solve it, and instead focusing on the past that will. So removing unnecessary detail, not focusing on detail that's not going to help you solve the problem. So that is, and we'll look at some examples in a second, but that is the sort of the main consideration there for abstraction. That is what it is. It's only focusing on the details that are important and just removing everything else, because then you don't have to worry about it. Right. So the next part is, and this is kind of just cementing that really, the abstractometer, the diagram down there, it kind of tells you. So this idea of abstract, if you take a heart on the left-hand side, being shot by an arrow, I don't know why someone's got a broken heart here, but anyway, it's too realistic because there's blood and gore. The middle one, you can still see it's a heart, you can still see it's an arrow. The right-hand side one, it's too abstract. So you're looking for that sort of Goldilocks zone where it's just right, where you're focusing on the right details to solve the problem. Because it can be overwhelming if you try and solve every single part of a problem in one go. Pick on the things that you need to solve to actually produce a solution, okay? So removing unnecessary details. If they do a 2-mark question, think about how you can break this. In fact, it's these 2 bullet points here. They sometimes do a 2-mark question on this. In which case, what you need to do is first of all focus on this bit here, which is first of all to identify the information that you need for the solution, and then secondly to ignore the details that you don't need to make the solution, right? So that's what they're looking for. So that is abstraction. And now let's go to, we've got 4 people in. Do say hello, guys. I can go back and do some quizzing later on if you fancy. Right, this is, surprise, surprise, a map of the London Tube network, as in the Underground, right? Now, this is the original London Tube map, and you can see that it's quite confusing, isn't it? It's got all sorts of very colourful lines on it, and it's quite hard to read, isn't it? So this was the original tube map when the tube was first built. This is what passengers were given to plan their routes. And you'll notice that it's nothing like the one that we use today. So then we go forward to 1933 when a London Underground employee, his name was Harry Beck. In 1933, he came up with this, which is the tube map that we use today. And I think that this is probably the best definition in practice of abstraction that you can see, that it's removing all of the unnecessary detail. So have a look at this map and you can see that it is a design classic. Now, what's clever about this is that if you are trying to get from, I don't know, where are we? Let's go to the bottom. This is where I used to live, down here, the bottom of the Victoria line, which is down here. My rectangle just down here. So if you're going from Brixton and you're going up to watch, I don't know, you're going up to Arsenal to watch Arsenal play because you'd be doing something sensible, look how easy it is to plan using this map. You think, okay, I'll take the Victoria line, I'll go up to King's Cross, and I'll change. Easy peasy, all right? No problem at all. But then look back at this map and see how much harder it is. And just for ease of reference, there is Brixton down here, and here is, where is Arsenal? Oh, actually, it doesn't help, actually. Arsenal, is it on my map? No, it's not. Arsenal's actually up here somewhere. It's actually up here somewhere. There's Angel. So it's kind of, that's not very helpful, is it? But you can see how it's so much harder to plan your route. So what is the difference? Well, the difference is that one map has used abstraction, the other map hasn't. What's interesting is when this, because Harry Beck, he wasn't being paid to do this in 1933. He literally sort of wrote this on a scrap of paper and took it in, and the tube network managers said, "Oh no, this map's way too complicated. No one's going to understand this. It's like something from a science fiction film." But of course, compared to the actual map, it's so much easier to read. But look at how it is so clever. It's abstract. Why is it abstract? Because all the details you don't need have been removed. And the question is, have they removed too many details? Do you remember that series of pictures of the heart that were being shown? If you've gone too far, it means that you can't actually do what you need to do. You can't solve the problem. The problem here is getting from A to B using the tube, all right? So you can see that a lot of details have been taken out. So, for example, things like, let's have a look at this one. If we go over to our map on the left-hand side here, you can see that these borough names have been taken out, like Kensington and Chelsea. The parks have been taken out. The roads, because where are the roads? The roads are all over the place here. Let's have a look at a few roads. There's a road. There's a road. And while it's handy to know that that is the Rotherhithe Road there, the A200, and that this is the A10 going up here past Dalston, all well and good, but you don't need it if you're on a tube train, do you? It serves no purpose at all. So that's where Harry Beck's map was so clever, is that all of this detail shown on this tube, you just didn't need it on that map. So instead, he produced this map on the right-hand side. And this is the sort of process that he went through. Green spaces. Do I need to show it? The answer is no. Roads. No. If you're on a tube, you've got no need to know what the roads are. Place names? No. Need to know what the tube stop's called. Borough names? It serves no purpose. An accurate location? And that's actually going back to here. You can see one advantage of this map on the left-hand side is that let's try and have a look at this one. If we look at the distance between, let's do a little circle here. Let's have a look at the distance between Covent Garden and Leicester Square, about here. Now, in reality, someone who's very, very quick could jump out and run between those two stops. There are YouTube videos of people doing this on the tube, and they could actually get to the station before the train arrives, having jumped off it. That's how close they are. They're literally 100 yards apart. And that's shown in this map because it's to scale. Whereas if you're down here, the distance between Brixton and Stockwell, it's about 4 or 5 miles, so it's a lot further. But if you look at Harry Beck's map over here, these distances, they're not reflected by how far they actually are in reality. But of course, if you're on a tube, you don't care. You just got to sit there and wait. So whether it's 5 miles or 10 miles, it makes absolutely no difference. So this over here, this represents all of the unnecessary detail that was removed because it doesn't serve a purpose. So all of this stuff here, there's no point in having it there because it doesn't make your journey any better. In fact, all it does is just make it more confusing to get from A to B. Oh, that's me again. It takes it more confusing to get from A to B because you've got lots and lots of information that you just don't need. All right, abstraction. We've ticked the box. The next one, 4 of you still in. Hello, hello, hello. Decomposition. Here is the definition. Breaking down a complex problem into smaller, more manageable parts. 1 mark, which are easier to understand. Possibly 2 marks. And then finally, the second bit that you need here is the smaller parts can then be solved individually. So I've tried to do this. I mean, it's hard to predict exactly what they do, but they do like to kick off paper 2 by making sure you understand what these mean. So there's two easy marks there, okay? So you've got abstraction and you've got decomposition, all right? So decomposition, breaking a problem down into smaller parts, which is obviously what you do. So you might, so in terms of a program that you're writing or an algorithm, you won't have to do this, but professional programmers, I mean, say, for example, if you're writing FIFA, you don't write it as one gigantic big program. You've got a team of people working on this bit, and within that team, you've got one person working on, I don't know, shirts. You've got someone else working on the sounds inside stadiums. Do you understand? So you can break it down and give people much smaller jobs to do. It makes it much easier to manage and means you can probably bring the project in on time and maybe within budget, which people care about a great deal. So here's a kind of almost primary school explanation of decomposition. So in this example, we've got the notion of making dinner down here. And let's just draw a little line around that. I'm sure you can see it anywhere. And look at, this is the problem being decomposed, okay? Making dinner. Okay, so making dinner. I don't know who's got time to make a starter, a main course and a dessert, but let's assume that you do. So you do that. That's the first bit of decomposition. So you could give, if you think about the system they use in restaurants, which came from France, this idea of having different stations in a kitchen where you've got a pastry chef, you've got someone cooking the meat, you've got someone cooking the fish, you've got the special orders chef, etc. You can see that here you've got make starter, make main course, make dessert, and then you can break making the main meal down into the meat course and the vegetable course, and then the vegetable course is going to have more moving parts to it. And so you can break it down and break it down and break it down until you've got a list of problems to solve. It was actually interesting. One of my sort of guilty pleasures was watching MasterChef. And there was a guy on MasterChef who I was watching the last series, and he was an accountant. And when he was doing his cooking, he actually had a spreadsheet which had task 1, task 2, task 3, task 4, task 5. And there was 50, 60 tasks on there that he had to complete inside the hour and a half. So he literally had used Excel to decompose his whatever he was cooking. So it was just a series of steps. Cook the asparagus. Next thing, take the asparagus, put it in chili oil. Whatever it is you're doing, okay? This is going to make me hungry, so let's move on. But that is the notion of decomposition. Now, algorithmic thinking. So when we try and write an algorithm or a program, we need to think about it as a clear sequence of instructions. That's what we're looking to do. And we're going to solve the problem in a step-by-step way. And we know that if you write an algorithm, the computer will spit it back out if you haven't written it properly. Obviously, in pseudocode, it doesn't matter, because that's just to give you an idea of what the program does. But what does it need to be? Unambiguous, complete, accurate, consistent, and efficient. Those are the definitions of what you're looking for in an algorithm. An algorithm can't work several different ways. It works in one way. It's got to be complete, or else you'll get, it'll crash. It's got to be accurate, or else it won't give you the information you want. Your approach and design has to be consistent all the way through, and it should be efficient. It should be as few lines of code in your algorithm as you can possibly do, because it's going to use less memory, and it should be memory efficient as well, okay? So don't worry too much about this, or especially the diagram on the right-hand side here. But that is what you're looking to do when you write an algorithm. And one of the interesting things that students try to do is they often try to overcomplicate the algorithms that they write, because they decide to not read the question carefully and try to give the examiner more than they ask for. Well, they're not going to give you any marks for that, okay? So this, again, it breaks down what brushing your teeth is, and I think probably we've done this one to death now. So thinking computationally involves breaking it all down, using those skills that we've got in terms of abstraction and decomposition, and getting on with it from there, okay? All right, now, yeah, I don't think we're going to manage to get through that bit, because I'll leave this on there for a moment. What about number 1? I can see there are a few of you still on here. Abstraction is the process of adding detail to a problem to better understand it. Does that sound like it's true or false? I'll just do a few seconds on that in case anyone jumps in and tells me. We shall see. But if you stay quiet, which it looks like you are, I'll just jump on to the next bit, and we'll go from there. Yeah, that's what I'll do. I'll jump on and I will do the next bit of teaching, boom, boom, which is here. All right, key terms. The reason I put this in here is we're starting paper 2. Paper 2, there's some basic programming terminology that you need to understand. You don't at this stage need to be an amazing programmer, but there is some terminology you need to understand so that you know what they're talking about when they ask you to do things. So let's run through these really quickly one by one to make sure you are happy with them. Take a screenshot of this. Obviously, I'll put a copy there for you on YouTube as well. So first of all, they will, at some point in the exam, they do it every other year. So they might do it this year because I didn't do it last year. They will ask you what a variable is. I always call it a box where you store stuff, okay? But in fact, to be technically accurate, it's a named storage location, and its value may change as the program runs. You've got a constant, which is exactly the same. It's a named storage location, so you might call it pi, and then you'll put in the value of pi. And for pi, it doesn't change, therefore it's a constant, and the value will not change as the program runs, okay? And it's that as the program runs that is really important. Jumping back really briefly to the variable, I just wanted to say that a good example of a variable could be score in a game. So the score will get updated. You start at 0. It'll initialize and go to 0. and that is down here. There we go, 2 for the price of 1. So when you create a variable and you give it a value of 0, it's called initialization. They sometimes give a mark for that as well. And so far, that's not hard, is it? It's that you create a box, you call it something, and you give it a value, 0. So score equals 0 would be how you might do that. Okay, so that's the first thing. Let's jump on and look at this next one, which is construct. It's a word that students seem to struggle to remember. Where have I got it? I've got it over here. So construct. Construct means selection or iteration. Those are the two constructs that you're going to worry about. Selection with an if statement, and iteration, which is a loop. And you've got to know both of those, okay? Then we've got parameters, and we'll come on to subroutines a bit later on. A subroutine is a reusable piece of code. So you write a piece of code, and rather than copying and pasting it again when you want it, you call it. So you write a piece of code, you give it a name, and then you call it when you want to use it. Because it might be you want to use that code several times throughout a program, and rather than just copying and pasting it, you can call it. All right, so that is a subroutine, a function, or a procedure. Okay, so arguments are the values that you put into functions. For example, an array is a fancy word for a list. You need to know how to make arrays. It's not hard. We'll come to that in a week or two. Concatenation is when you join two strings together. So, for example, they might ask you to write an algorithm that takes in the user's first name and their second name, and then write a piece of code that joins the two together. Well, you use a plus. That's what concatenation means. Fancy word. It just means adding two things together. Declaration is the data type you give your variable. So it could be a string, it could be an integer, however you want to declare it. Assignment is giving it a value. And initialization is giving it a value of 0 to start with, which very often is what you do. Not always, but very often what you do. So depending on how comfortable you are with these terms, I would say it's probably worth making sure you're happy with those. Because paper 2, students mistakenly often think that it's just about coding. It's not. It's only about a third of this paper that's really coding. A lot of the rest of it is just principles about how you might code rather than writing code. So there's a sort of difference there. Right, I wanted to have a look at this. This is a scenario that I wrote, which is based on a past paper question, an OCR past paper question. And this is Dreamville is, and by the way, why are we doing this? Because I've talked about abstraction and decomposition. We're now going to use this on a sort of question that you might have in section B of paper 2, which is the more tricky one, where you've got to write things in pseudocode or in a high-level language. Okay, so Dreamville is a theatre aimed at children and adults. Tickets are sold online. Adults tickets cost $19.99. Child tickets $8.99. A booking fee of £2.50 is added to all orders. I've ripped this off a question. A function ticket price takes the number of adult tickets and the number of child tickets. Those are the parameters. That's the data you feed into your function. It calculates and returns the total price. So the first thing that I would do when you're faced with a question like this will be a 6 to 8 mark question. So there is a grade boundary on that paper for this question. So it's worth taking a bit of time. So I would go through it again and make sure I understand it. Okay, so you've got 2 tickets, a kid's ticket and an adult's ticket. Right, that's fine. Every order you add £2.50, a bit like Ticketmaster. And they've written this piece of code, a function, which takes the number of adults and the number of child tickets. So it might be 2 adults, 2 kids. So it'll take in 2 and 2. It'll then calculate and return the total price. If it was 2 adults, 2 kids, it'll be the 2 adults would be 2 times $19.99. The 2 kids would be 2 times $8.99. That's what I would do first of all, is just make yourself comfortable with this problem and think, okay, I know what they're asking me. Can I write the code for it? Or can I have a go at writing as much of the code as I can? But if you don't go through this phase and try writing code straight away, it can get really difficult really quickly, okay? Okay, so let's say, for example, we had 2 kids, 2 adults. It would be 2 times 19.99, which is £40 less 2p. and 2 times 9 quid, which is £18 less 2p, 17.98. Right, so we've got those two would then be added together, and then we're going to add £2.50 for a booking fee. Cheeky, isn't it? Booking fee. Use pseudocode to create an algorithm for the function ticket price. So I know that what I've just done there is neither abstraction nor decomposition. I just think it's common sense that when you look at a question, I mean, how long did that take me? A minute? Just to go through it and go, okay, I can see what's happening here. I've bought stuff online, so have you. We know how this thing works. All right? Okay, so next stage is let's actually do some abstraction and remove the unnecessary detail. OCR are horrors for writing questions that are unbelievably long. And you can often die of boredom before getting to the end of one of these questions. So look at what I've done here. I have removed the unnecessary detail, also known as abstraction. And look at how much of this I've got rid of. Dreamville, we don't care. Theatre, we've got no interest. Children and adults, tickets being sold online, don't care. Adult tickets are 20 quid, we need to know that. Child tickets, £8.99, we need to know that. Booking fee of £2.50, all orders. That's it, isn't it? You've got adult, child, and a booking fee. That's all we need to know from that first paragraph. All the rest of it is just waffle. Next bit, a function takes the adults and the kids and returns the total price. Write an algorithm. Okay. Now, that for me reduces the number of tasks that I have to do. It also means that I'm now dialed into this question. I think I can write some stuff for this. I think I can get, and that's where you've got to be. It's like, okay, I think I can get 4 marks for this. I marked a lot of my students. I think 3 or 4 of my students in year 11. They just left their page blank for this, and that's a blank page will get you no marks. But if you can begin to get your head around it, and I think the important thing is just spend a bit of time getting to know these questions, because actually, once you've read it for a second time, you'll find yourself going, oh, okay, it's a bit of take this and take this, add or divide something, or if it's bigger than this, do that. If it's smaller than that, do that, and then print something on screen. That's all that these questions are. They really do ask you the same thing again and again and again. Right, abstraction. So this is my abstracted question, which is we've got 2 tickets, one at that cost, one at that cost. There's a booking fee of 2.5 quid. Write a function. It takes in the parameters of adult and child. And if you're now going, oh, he's using that parameters word again, let's spend a minute on this because I think it's really worth it. Is that, let's get to here, the parameters, right? A function is a reusable piece of code, so you can call the function. So that means someone's written this code, but you need to give it some information. Well, what information does a piece of code which is working out the cost of tickets need? It needs to know how many adults and how many kids are travelling. That's all it needs to know. So therefore, those are your parameters, and they will be separated by a comma. So it might be 2,1, which would be 2 adults, 1 child. Do you understand? So that's the only information that this actually needs, this algorithm, is to know how many adults, how many kids. Calculate total price, return total price. Where are we time-wise? past, okay. All right. So I'm hoping that having done that, you then may look at it and go, well, I can probably do a few of those things, but let's not get there yet. Let's now look at decomposition, which is breaking it down into steps. So decomposition is we're going to break it down into a series of small steps that you can solve really, really easily. 8 of you in, hello. Task list. Write the function. Now, if you don't know how to write a function, that's going to be a problem. But as you will see in a minute or two, writing a function involves writing the word function, which on the face of it isn't that bad. You're then going to say what the parameters are, 1 adult, 2 children. You're then going to work out whatever the maths is. We're going to times the adults by 19.99, the kids by, was it 8.99? Yeah. We're going to add £2.50 because Ticketmaster love to do that, don't they? Although £2.50 would be cheap for them. We'll calculate the total price and we'll return the total price. Now, this is very complicated, but when you write a function, when you return something, wait for this, it's very hard. You use the word return, okay? challenging, isn't it? So literally, you could go away and learn how to do a function in 5 minutes. It really ain't hard, trust me. It's just not difficult. So that is me having broken this down into 4 tasks that you need. And because I'm nice, I even wrote a little sort of the information down here to show you what it is that you need to do. Okay, so that's the information for you there, and there is your task list. So we have now decomposed that problem into a set of 4 tasks, and hopefully if you can complete 1 or 2 of those, suddenly you're scoring on these questions, and people are scared of them. Programming, ooh, it's scary. It's not really. You might not get full marks on this side of the paper, but if you can be scoring 3, 4, 3, 4 on these 6-mark questions, suddenly your grade just starts to elevate. And this is what most people find the trickiest, okay? So now let's break down. Let me go back to that one very, very quickly. Let's turn it into an algorithm, so algorithmic thinking, okay? So first of all, we need to know how to write a function. I'll explain that to you. And in fact, this will be useful. I'll try and cover this again before you actually have your exam, but writing a function is so easy. Then we're going to focus on the inputs. Whatever they ask you to do, it'll involve inputting some kind of data. And usually it's asking the user to enter something, and there's a piece of code we can learn for that. And then at the end of it, you'll output something, which usually, not in this case, but usually means using the word print. It'll be return here because it's a function, but hey-ho. Then we've got the variables we're going to look at. What boxes do we need? So that is over here. What boxes are we going to store things in? It's a named location in memory, which is given a value. Could we initialize it, set it to 0, for example? What about the processing? And that means, what about the maths? The maths and the logic. Is there any multiplication, timesing, division, or subtraction going on here? Yes, there's some multiplication because you've got 1999 times however many adults. We've got 899 times however many children. And then we're sticking on £2.50 for a booking fee at the end. So a little bit of maths there. No Boolean logic, no greater than, no less than, no not equal to, none of that stuff. Then we'll think about the constructs we want to use for this. And that means, are we going to use an if or are we going to use a iteration of some description, okay? And then think about the outputs. And the outputs here is writing the word return. Okay, so let's jump in and see how we can fix this. And I'm hoping that doing it in this way might make it a bit easier for you. So just to help you, the stuff in purple, that's the pseudocode that they'd actually want to see, okay? So first of all, if you're writing a function, and very often they give you a mark just for these 2 steps here, they give you a mark for writing function, and wait for it, I'm trying not to be patronizing, but it is quite easy, and then you write end function at the end. There we are. So there's not a lot of thinking there, is there? You just write function, leave a few lines, and then write end function. So now you've created a function. Okay, next step. You give your function a name. So for example, tickets. Function tickets. And then look, here's something else that we looked at a minute ago, which is parameters. And that's going to be 1, 2, 1 adult, 2 kids, 2, 5, 2 adults, 5 children. And then down here is where you do your maths. So that's where we're going to sort of times one by 1999, times the other by 899, and then add £2.50. And don't forget your bid maths. Bid maths works. Everyone loves a bit of bid maths. So don't forget to think about the order in which the calculation needs to happen. And then you return the result. So literally, that is a function. In I think the last paper but one, they put in 3 or 4 different function questions. They really probed with functions. So if they do it this time, that is such an easy way to pick up marks. And you can do this with a very limited understanding of programming, okay? Functions are very straightforward things to write. Incidentally, one of the things I love to ask is, what is the difference between a function and a procedure? Well, there's one really key difference, and it is this, that a function returns a value to the main program, whereas a procedure doesn't. So here, this return line is when it takes it's done some maths and worked out your answer, and then you take that result, which is stored in a variable called result, and you then do something else with it. A procedure just prints the result on screen. And that's usually the end of the program. Not necessarily, but usually, okay? So that's the difference. A function returns a result to the main program, a procedure doesn't. And they love that question. So just think about it today. If you go back and have a look at this and make sure you can write a function, give it a name, what are the parameters, write your code, use the word return with the variable that you're going to return, and write end function. That's it. If you've got that, you could get 4, 5, 6, 7, 8, 9, 10 marks in the exam, okay, which is huge. Also, think about the importance of just breaking this down into steps. It makes a massive difference, okay? All right, so that is your functions there, 34. Right, so I've written function ticket price. That's what I've called it, ticket price, because I'm very clever, so I called it ticket price, all I've done so far. So now I'm going through it in order to show you what you would do. So that would get me probably 2 marks. I've then gone function ticket price adults and kids. So those are the 2 variables that we're going to use. So we are literally going to suck those 2 variables into our function. The function drags in those 2 bits of data, and inside those 2 bits of data will be stored a number. So someone will have said that there are 3 adults and 5 kids. So when that gets dragged in there, inside the adults variable and the kids variable will be 3 and 5, okay? Then we've got our programming code beneath it. All right, let's push on. Return price. Price down here, let's use my little thingy bob. Price down here is and by the way, you could use any name here, but price is the name we're going to give the variable for the final cost. Could be cost, price. Name your variable something sensible. That way you know what they actually do. Okay, and then end function. All right, so let's get rid of that. And let's go on to the next bit. Number of adults and number of children are going to be our 2 inputs, all right? And we're going to declare variables. So whenever you start writing code, I would think first about the input. Are there any user inputs? You can write the piece of code for that to take in a number or a name from people, a word. And then what about variables, the boxes that you're going to store all of the information? So I would scan through the question and think, okay, what boxes am I going to need to store stuff? So I'll make a box called that, a box called that, and a box called that. And then you can add those boxes together. You can divide what's in those boxes. You can display them, print them on screen. You can do calculations with them. You can do math and you can do logic with them. So that's, once you've done that, talk about deconstructing a problem. It becomes far less stressful when you think about it in terms of, I can do inputs, I can work out the math and the logic, and I can do an output at the other end. And that's what you really need to do here. Okay, so that is number of adults and number of kids. That's going to be the variables that we'll create. So this is what I'm going to call these variables. I'm going to call number of adults adult. I'm going to call number of children child, and I'm going to call total cost price. So I've now made my variables, and then we're going to do an input. Adults equals input enter adults. Kids equals input enter children. And that piece of code, if you can go away and learn that simple input, this is where people on the screen would appear these 2 words here. So if this program was run, just these 2 lines of code, what you'd end up with is, on screen, you'd end up with this appearing, enter adults, and someone types 2. And then you press enter, and the next line of code, it says enter number of children, and you type in 2. And then 2 and 2 are stored inside adults variable and 2 inside the kids variable. So thinking about these boxes in which you're going to store stuff, please don't use the word boxes in the exam because the examiner won't like it, but it's much easier to understand. So think about the boxes where you're going to store this stuff. All right. So let's now think about the maths here, the processing that's going to take place. I'm assuming that you know that this guy here is multiplication, the asterisk. So it's really simple, isn't it? No logic required here. So when we work out the adults, what we're going to put inside the adults variable means the number of adults times 1999. 1 adult, 1999, 2 times 1999, 3, and so on, okay? Kids times 899, and the final price is whatever you have now stored in the adults variable, which will be the total cost for adults, plus the total cost for kids, plus your £2.50 booking fee. Okay, so that's all that you really have to do there. That's the processing. What's interesting, I'll rephrase that because it's not interesting at all. What is true is that they they often give a mark for attempting to do the processing and a mark for getting it right. So I know clearly all people who mark exams are employed by Satan, but actually it's not really true because they're trying to mark positively. That's what they're asked to do. If they can see that you've tried to get your head around the question, you've got some knowledge, they will always try to give you marks for it. The aim isn't to give you as low a mark as possible. I know it might seem that way sometimes, but that's not actually how it works. And then the outputs, price equals adults plus kids plus £2.50. We've just done that. So here is the final function. Now, if you are scared to death of coding, and this is the first time you've sat through something that long about how to write a function, how do you feel about that? Have you looked at bits of it and gone, that's actually quite easy? There's very little that you need to learn to make sure you could write this question out and get full marks, really. So function ticket price, then I've got my two parameters, adults adults, comma, kids. Price equals adult times 19.99 plus child times 8.99 plus £2.50. Return price returns that variable price to the main program, and then the function ends. And think about if, end if, while, end while. Okay, it's similar for all of these constructs that they just put an end at the end of it. Okay. Right then, algorithm practice. If any of you who are here, I can see there are 8 of you currently in. Any of you got any questions on that? Give me a shout, okay? But that was a whirlwind tour of what you need to do to write a program, an algorithm. Let's have a look at this one. Same again. GT app tracks users' average and maximum heartbeats. Users enter, here's the input. Users enter average and maximum heartbeats displayed on their fitness watch. Okay, so the user's going to type in like 95 average heartbeat, maximum heartbeat 120. If the average heartbeat is between 0 and 90, which would mean that you're sitting down probably, a message lazy is displayed. If the average heartbeat is above 90, the message good is displayed. If at any point the maximum heartbeat is above 176, the program stops running and an ambulance is called. No, it displays the message seek medical advice. Yeah, that would be the least of my worries if my heartbeat was 176. But anyway, along with the average and maximum heartbeat of the user. So again, it's one of these long, convoluted questions. Now, I wrote this one, the one that OCR will write for you, and they do this on purpose. They give you a wordy problem, and your first job is to go through it with your sort of your correction pen and go, that's not relevant, that's not relevant, that's not relevant, that's ridiculous, I don't need to know that. And you just focus on the stuff that you need to do, okay? So again, abstraction, decomposition, okay? So abstraction is the first phase we will look at now. Again, because I wrote this, it was a fairly short question, but there's still a lot of stuff in here that you don't need to know. GT app tracks that. Boring. Displayed on their fitness watch. We don't care. Message. We don't care. Actually, the rest of it, we probably do need to know something about, okay? So here we go. Now you're not going to have time in the exam to write this out again, but you will have time to use a light, to use your pen, just to draw through the stuff that you don't need to worry about. The details you're not going to focus on for this question. So users are going to enter an average and maximum heartbeat. So we need to input some data. Okay, so you've got to learn the code for inputting data. If the average heartbeat is greater than 0 and less than 90, print lazy. If the average heartbeat is, hang on, that looks like selection to me. It's an if statement, isn't it? So an if statement is when if this is the case, do that, else that is the case, do that, else that is the case, do that. So it's a decision where you've got several possible outcomes. So that would be an if statement. Again, figure it out. Does an if statement work here? Yeah, it does. If that, do that, else do that, but else if do that, else do that. Yeah, that's perfect. And then we've got so the printing. So it's either going to print seek medical advice, that's if your heartbeat's over 176, or it's going to print the average heartbeat, or it's going to print the maximum heartbeat. So we've got a series of output commands. and an if statement in there. And that's all this thing consists of. Now look, you might get it wrong. You might pick the wrong construct. However, you can see that it's actually really simple once you've broken it down into such a series of small steps, okay? It makes it so much easier to do. Right, decomposition, break into smaller tasks. We've got 3 tasks to do. Input average, maximum heartbeat, do comparison using an if statement with the correct message, and end and print the message if maximum greater than 176. Okay, so that's all we've got to do. Just a couple of steps there. So how do we turn it into an algorithm? And again, this is how I would always do these. The input at the top here that I've put up here, let's do over here, inputs. When we've got the inputs, I would focus both on 2 sets. I would think about, first of all, taking user input, but I would also think about creating your variable. In fact, I've got creating variables as number 2. So let's stick with it this way. Inputs are taking user input, okay? And you've got to learn that line of code for it. You'd have seen it dozens of times. Then we do our variables. Then we do our processing. Think about the constructs we're going to use. Again, is that selection or iteration? We've said selection, which is your if statement. And then the outputs. All right. So the inputs are going to be average heartbeat and maximum heartbeat. Those are the 2 inputs you need to worry about. So we'll set those. Average heartbeat I'm going to call AHB, and maximum heartbeat equals MHB. So that's what I'm going to call those 2 variables. And here is the piece of code that you need to learn to input data. And honestly, this is just worth making sure you know off by heart, because I think in the last exam there were 5-6 marks because they kept, every time that they write a piece of, they ask you to write an algorithm, they want user input, okay? So this is how you might do it. Remember AHB, let me use my little highlighter here. AHB is, there we go, whoops. AHB equals input. So I called it AHB over here. You could call this whatever you liked. Equals input, average heartbeat. So on the screen appears the phrase average heartbeat. Someone types in 98, and that gets stored here in AHB. Okay. Equally, if we look at the next one, which is MHB, which is maximum heartbeat, exactly the same thing. Input, maximum heartbeat. So you need to go away and learn that line of code. That's worth 4, 5, 6 marks in the exam. It was worth more in the last one, okay? So that's the inputs done. Next, we'll focus on, in fact, those were the only variables that we need. And bear in mind, I'm saying inputs and then variables. You are actually creating a variable when you do this, because you've created a variable called AHB, and you've created a variable called MHB, all right? So that's important to remember, that this line of code actually does several things. First of all, it creates a variable called AHB. It also makes this message appear on the screen, and it also saves whatever the user types in response to that message. It saves it inside this AHB variable, which is a named location in memory, which has a value or can be assigned a value. All right, so that is really important there. Okay, logical comparisons. Let's have a look now at the processing part of this and think about the comparison, okay? So comparison of BPM, and we're going to use an if statement, and we're going to use a while loop as well. Now, the while loop is a slightly more advanced bit of programming that we're going to do here. And the while loop is very often used when if one event occurs, then the program stops running, or this is when you want to move on from a block of code. You might use a while loop for that, okay? So in this case, while your heartbeat is below 176, everything's happy. But as soon as it hits 176, you get that message and the code stops running, okay? So now that's looking at our construct. So the while loop, And by the way, I would just use the while loop. And that means that all you've got to know is the while, end while loop, the if, end if loop, and then you're done. Yeah, there's some other text manipulation stuff that you'll need to know, but it's not that hard. Things like opening a file is open, closing a file is closed. There's a bit more to it than that, but fundamentally, if you can figure out when to use an if statement and when to use a while loop, you've actually cracked the programming part of this paper. I know that sounds crazy. I don't know how it takes us 3 years to teach you this, to be honest with you, because it is. The difficulty is wading through all the waffle in these questions. That's what's so challenging. Right. So here we go. This is the if statement now. This is selection. And again, just like the function I showed you, every if statement is going to look like this. So let's focus for a second on this if statement. They all look like this once you strip out the numbers that I've got in there. So if this is the case, do that, else do that. And if you've got sort of 3 or 4 or 5 different alternatives, you're going to use else if, else if, else if. And the else, the else you can see here, this is always the last condition, okay? It always ends with an else, and then you actually complete it with the end if. Again, notice that, if, end if, while, end while, function, end function, procedure, end procedure. It's all the same. Okay, so whatever I say and whatever your teachers have said to you over the last 3 years about coding, there really is no substitution for just looking at a piece of code and being a little bit determined and resilient to understand it, because it's not easy. This is computer science, not colour by numbers. So, it is difficult. So let's have a look at this piece of code to make sure you're happy with it. So first of all, we've got, if this condition is true, if the average heartbeat is greater than 0 and less than 90, then print lazy. Tick. So we get a mark for that. Probably get a second mark for using an if statement and actually doing the comparison correctly. And I'm sure you're happy with these greater than and less than comparison operators there. Then we've got else. If the average heartbeat is greater than 90, then print good. End if. Okay, that's your if statement. Done and dusted. Easy peasy. We've still got one more bit to do, haven't we? And that's if the heartbeat is very high, then we stop the program running and we call for medical help. And we're going to use the while loop for this. So while MHB, maximum heartbeat, is less than 176, run the code. In other words, if you put this piece of code, not quite at the top, but very early on, it means you're going to run that selection, you're going to run the if statement, you're going to run it really happily until it hits 176. And then we'll look at the code that you're going to run. But this while loop, that is really the last place that you need to go, is can you figure out where to put a while loop in and when to use a while loop. I know we've got for and we've got while, but just use while. Recognizing for is important, but that's all you have to do. So now look at the whole piece of code there. Can you see that I've put the while loop? I've put it at the start, and I've covered the entire if statement with it. That's really explained badly. It sits, let's try this. The if statement sits within the while loop. There we go. That's much more logical. Okay. So you can see that if statement, that selection, the construct selection, is going to run only as long as we don't hit 176, because that's the point at which things need to change. So look how easy that is. Oh, and I forgot to mention this extremely challenging piece of code, which when you write a while loop, you start with the word while, and it ends with the word, not 2 words, the one word, end while. That's it. That's all you've got to do. And very often you look at the mark schemes and it'll say, using a while loop, 1 mark. And it might be that they wanted something else, but if you've had a go at it and you've thought about it logically, you can probably find you can score a lot more marks on this paper than you thought was ever possible. Where are we? 54. We're getting towards the end here. Print AHB. Oh, this is the output statements. Again, a lot of people leave it blank. Just, if it's going to be output, it's probably print. print on screen. So print that variable, or print seek medical advice. Those are the outputs that we're looking at, okay? And here we go. Here's the entire thing together, okay? So that's the entire sort of system there. And can you see on the right-hand side here, and again, I don't know what level some of you, I know that you've, like most classes, there are some of you who are quite comfy with programming and some of you who find it a bit bamboozling. Well, this over here, I found this really helps students, is just to, when you're doing your, we talked about abstraction, we talked about decomposition. When you're doing your decomposition, these areas here, these are your tasks. Sort out your inputs, sort out your constructs, think about your processing, and then do your outputs. That's it. And if you focus on one at a time, it's really easy. Advice for you. People often find flowcharts easier to write, and in section 1 of paper 2, you can use flowcharts. But if you're going to use a flowchart, and my advice to you would be maybe don't, because on the face of it they look simple. But the problem with the flowchart is if you don't plan it, you end up writing it and then having to rewrite it, and it takes ages. So if you do use a flowchart, actually plan it before you write it. Literally make some notes about what you're going to do so the thing makes sense in your head before you commit to actually drawing all the symbols, which takes time. But my advice to you would be try and do it in pseudocode. It's quicker and you can get the marks. People tend to score better when they write things in pseudocode. And sometimes, once a problem becomes slightly more complex, doing it as a flowchart actually becomes quite hard. There are so many moving parts to it, so just bear that in mind. So this is the final piece of work we've got. And again, I'll just run through this up here. Can you see that we've taken our inputs here? First thing we did, this is what the user's going to input. They're either going to input their average heartbeat and their maximum heartbeat. Then we used, the next thing we did was that we used the while loop, which encases, that's a better word, which encases our if statement here. Okay? And look at the use of indentation. And indentation means, think about this, where's my arrow? Think about this gap between here and here. It makes the code easier to read. There's a mark for you on writing code there, because they ask you about how can you make code easier to read. Use of indentation, and that's what your program will. We'll get to that later on, but you can see that makes it so much easier to read, doesn't it? Okay, and then you've got the outputs down here, which are all these print statements. Okay, all of these print statements here, here, and here. What I'm really hoping is that if you adopt this more sort of formalized process, this more structured way of writing algorithms, you'll find that you're getting far, far more marks. It seems like hard work on the face of it, but it's just having a strategy that you can bring to bear on these types of questions, because they are without a doubt the questions that students find harder. Paper 2 is the one that gives people absolute nightmares. All right, it's 18:57. I'm going to stop. I do have quiz questions, but I don't think there'll be any quizzing today because no one's answering any questions. So when I next see you, you'll have been back in school Monday, Tuesday, Wednesday. So do speak to Mr. Godfrey and ask him if there's anything you want me to cover, any areas you're particularly concerned about. Let him know and he can let me know and I can cover those. But my plan otherwise is now to go through paper 2 and teach you as much content of that as I can. Okay? Have a great holiday and I'll see you all in a week's time. Cheerio. Bye-bye.